Hello everyone and welcome to this introductory video about qMTLab. In this presentation I will briefly introduce qMTI and qMTLab and show you how you can use it. So first of all, what is qMTLab? Briefly, well, it's a set of tools with a graphical user interface for quantitative magnetization transfer imaging. You can use it for data fitting, visualization, analysis, and simulation. It's an open source software that we think it's very flexible and easy to use, and that is built in MATLAB. And for more information about qMTI and qMTLab, I'll refer you to our 2016 paper in Concepts in Magnetic Resonance, that you have the reference here. So first of all, why have we developed qMTLab? Well, quantitative magnetization transfer imaging offers a distinct contrast mechanism that is sensitive to tissue molecular composition. It allows the extraction, quantification of distinct tissue characteristics with high reproducibility and specificity to macromolecular content. And we think it's a very valuable technique, but however its use has mostly been restricted to researchers that have developed these tools, partly because the need to write complicated in-house software for modeling and data analysis. And for this reason, we think that by providing a free software that it gives the end user a simple and easy to use graphical user interface, we hope that to make qMTI accessible to a greater number of investigators and facilitate the development, the evaluation, the optimization, and of acquisition protocols and analytical models. So before we begin a review of qMTLab, let's briefly consider what magnetization transfer imaging is. Magnetization transfer basically refers to the interaction between the freely moving protons and the restricted protons that are bound to macromolecules. And by modeling the exchange between between the liquid and the macromolecular pool of protons, qMTI allows the measurement of precise information about tissue composition. For example, the fraction of the restricted to the free pools, the magnetization transfer exchange rate, or the relaxation rates. Most qMTI methods are based on the two-pool tissue model that was developed by Enkelman back in 1993. This model is characterized by a number of different parameters, like the pool size ratio, that is defined as the ratio of the size of the restricted pool to the free pool. You have the exchange rate, either forward or a reverse exchange rate, and also the longitudinal and transverse relaxation time or rates for both pools, and the size of the pools also. And the idea is that a signal equation can be developed and fitted to the data to extract these parameters here. So qMTLab currently supports the most widely used acquisition methods and analytical models. So we have these three methods here, the MTSP-GR, which combines enough resonant pulse saturation of the restricted pool with an SPGR readout. And there's a selective inversion recovery sequence that uses a fast spin echo readout, and also a BSSFP method that uses the standard BSSFP acquisition protocol, but using large flip angles and short TR to maximize the MT effect. So how do you use qMTLab to fit your data? Well, first you have to define your sequence protocol. So to do that, it's very easy to define it using the graphical user interface. So you can set your protocol, for example, set the empty pulse shape. You can save your protocol and save it to reuse it a later time. And for example, if you always use the same protocol in your institution, you can replace the default prot.mat file that comes with qMTLab. By this way, every time you will launch qMTLab, your preferred protocol will be loaded automatically. Once you have your protocol set, you can also use qMTLab to define your preferred fitting option. By default, the fitting options that are used there should be fine for most users, but should you want to play around with them and try different fitting parameters, you can easily use the software, the interface to change them. For example, you can choose the model you want to use for fitting, select the line shape of the restricted pool that you want to model. You can choose to keep certain parameters fixed. For example, the R1R value is often fixed to 1 in the literature, but sometimes some authors prefer to set it equal to R1F, so you can choose to do whatever you want here, or try to fit it directly if you wish to. And then again, you can save your preferences for later use, and if you save them by replacing the default fit options .mat, these fit options will be loaded automatically every time you launch qMTLab. Now that you're ready to fit, you can import your data. So if you put all your data in a single folder, save this, select this folder as your working directory, all your file will be loaded automatically. If you have defined a protocol and fitting option in there, they will also be loaded. So you can use qMTLab to preview your different maps. And also, if you want to preview the fitting, fitting can be long for a large data set. So if you want to just preview, you can select a certain voxel and fit for it. And for example, if you want to try different fitting options, you can do that by fitting repeatedly over the same voxel and see what the fitted curve looks like. And once you have defined your fitting option and you are ready to fit, just hit the fit data button, and qMTLab will fit your data and save it automatically in the same working directory. So once your data is fitted, you can use qMTLab to view the results. So you can choose the parameter maps you want to preview. You have the options to change the color map, change the range of the color map. Once again, you can select a certain voxel and view how the fitted curve looks like for this voxel. So if you see something interesting or something suspicious, you can easily look at the data behind it. You also have the option to open your 3D data in an external viewer for easier navigation that shows you the 3 orthogonal views. You also have the option to plot the distribution histogram of the current data, and view the value for a certain voxel that you select, and like I told you before, view the fitted curve for this voxel, for example. So now onto the data simulation part. This may be for more advanced user or for researchers. It can be very useful to generate synthetic qMTI data to evaluate how well different methods and models perform on the known ground truth, and maybe determine what are the most appropriate acquisition parameters, or evaluate how the fitting options and constraints impact the results. So in qMTLab we have three modes of simulation that are the single voxel curve, the sensitivity analysis, and the multi-voxel distribution. And I will present here. So the single voxel curve, it's where you can simulate empty data for a single voxel. So you define your protocol, you define your empty parameters, that is all the parameters of the tuple model, and you generate the data. Data is simulated by solving the block equations, so they are independent of the model that you use for fitting. And once the data is simulated, you can, for example, add noise to this data and see how the fitting perform under more realistic values. You can change the fitting option, for example, choose different model and update the fit and see what the fitted results are. So now at the top you have a table that shows you what the true values were, what the fitted values are, and what is the percentage error between those two. Now for the sensitivity analysis part, this is where you can simulate data by systematically varying one empty parameter at a time while keeping all the others fixed. So you select which parameter you want to vary, you set the minimum and maximum values and step size. Now every time a voxel is, the data for a voxel is simulated, Gaussian noise is added and the fit is run multiple times to allow the evaluation of the variance of the fit. And once it's done, you can select the independent and dependent variables on the plot results here to show to see how the variation of one parameter affect the fitting of another one. Now for the multi-voxel distribution, this is maybe a more realistic situation that you would encounter in real tissue. So this is where any parameter combination is allowed to be varied simultaneously. So you define the distribution for each parameter. You choose the number of voxels you want to simulate. You select which parameters you want to vary and set their mean value and variance for each of these parameters. Once the data is generated, you can analyze the result in a number of ways, using, for example, histograms or scatter plots of the input versus fitted parameters, or error histograms, bar graphs. Now, how can you integrate qMTLab in your pipeline? And it should be fairly straightforward. There are no complicated installation procedure or dependencies. Basically, you just download the software, extract it to a folder somewhere on your computer, and add this folder to your MATLAB path. You can also use qMTLab in MATLAB scripts. For example, if you don't want to use the graphical user interface, you can easily fit your data using a single line of code. Also, using the user interface, you can load matfile or nifty files directly. And also included in the software are external tools for file conversion. For example, there are tools for nifty or analyze image conversion, or a DICOM to nifty converters. So what is coming up next? Well, qMTLab is still under active development, so we plan to add additional MT methods in the near future, for example, MT-SAT or MT-R. Something I'd like to implement also would be a parallel computing support for faster data fitting and simulation, and maybe even your own contribution if you want to add something in there. We welcome all comments, suggestions, and improvements. Please submit them on the GitHub repository. So you can use this address here on GitHub to download the qMTLab for free. And once again, if you would like to have more information about qMTI in general, the theory behind it, and on the qMTLab software, maybe know a little bit more about the internal structure of qMTLab, I refer you to our 2016 paper that you have the reference here.